Previously, we have learned to find the covariant derivative of tensors. Okay. Now, in today's very short lecture, we will see a process for finding the intrinsic derivatives of tensors. In fact, when you talk about the intrinsic derivative of a tensor, you should note that this derivative is always defined along a given curve. Okay. So how we can define the intrinsic derivative of a given tensor along a given curve, we will learn in this lecture. And for this, let us consider that this A with superscript J1, J2, so on J alpha and subscript K1, K2, so on K beta, this is a mixed tensor of type alpha beta and rank alpha plus beta. Okay. And let us consider that we have to define the intrinsic derivative of this tensor A along a curve defined by this equation x to the power L of S. Here you know S is the parameter in accordance with which the coordinates x varies. Okay. So the intrinsic derivative of this tensor A along the curve XL of S, this is denoted by this symbol. This is denoted by delta A by delta S. If A is the tensor and S is the parameter on which the equation of the curve depends, then this intrinsic derivative is denoted by this symbol delta A by delta S. And how it is defined? Actually, if your aim is to find the intrinsic derivative delta A by delta S, then you have to take the inner product of the covariant derivative of this tensor A with respect to L and this factor dxl by ds. So if you will take the inner product of the covariant derivative of tensor A with respect to L and multiply it by dxl by ds, since we are taking here inner product, so it is called intrinsic derivative. Okay. So in this process, what we will have to do? First of all, we will have to find the covariant derivative of the tensor, and after finding the covariant derivative of the tensor, you have to take the inner product of the covariant derivative of the tensor with this factor dxl by ds. In this way, the result obtained is called the intrinsic derivative. So if you have an idea of finding the covariant derivative, it means you also know how to find the intrinsic derivative. But this intrinsic derivative is very useful concept in general relativity. When we will discuss the proper theory of general relativity, you will see at several places we will have to take the intrinsic derivative of different tensors. Okay. So how you can find the intrinsic derivative? The first step is, first of all, we will find the covariant derivative of the given tensor. Okay. And after finding the covariant derivative, we will multiply this covariant derivative and this factor dxl by ds. Okay. And this inner product of the covariant derivative of the given tensor and dxl by ds, that is called actually intrinsic derivative of the given tensor. Okay, along the given curve. So I think you have clearly understand how this intrinsic derivative is denoted and how it is defined. Okay, and what we will have to do for finding the intrinsic derivative of a given tensor. Okay. Now, after knowing this basic meaning or basic definition of intrinsic derivative of a given tensor along a given curve, now we are going to see how we can find the how the intrinsic derivative of contravariant vector, covariant vector, a scalar, or fundamental tensors can be defined. Okay, so one by one, now let us see. First of all, we will define the intrinsic derivative of a covariant vector. Okay, you have seen the definition, so apply the definition for this covariant vector. You will get the intrinsic derivative of covariant vector. But as I have told you, whenever you will have to find the intrinsic derivative, first of all, you will have to find the covariant derivative. And then you take the inner product of that very covariant derivative with the factor dxl by ds. So for this, let us consider that this aj, here you can say, see that this j is the covariant index and this is a covariant vector. Okay. And if you want to define the intrinsic derivative of this aj with respect to s, then how it will be denoted? You have seen the notation for it. It is denoted by delta aj by delta s. This is called the intrinsic derivative of aj with respect to s, where s is a parameter, okay, for the given curve. And how it is defined? You have learned that if our aim is to define the intrinsic derivative of this covariant vector aj with respect to s, then first of all we will find this covariant derivative of aj with respect to l. This a, j, comma l, what is this? We have learned earlier that this is the symbol for the covariant derivative of this covariant vector aj with respect to l. And we will multiply it by this factor dxl by ds. But you can remember what you have learned earlier. When I have discussed the covariant derivative for finding a covariant derivative of a covariant vector, then you have seen that this aj comma l, which means covariant derivative of aj with respect to l, that is defined like this. This equal to this much. This is del aj by del xl minus this second order, or so not order, but second kind Christoffel symbol times am. Here this m is the dummy index. At the place of this m, you may write any symbol. For example, if you write this as this gamma sigma jl, okay, and a sigma, that will be all right. So instead of m, you may write any symbol. Okay. So this is the value of the covariant derivative of aj with respect to l, or with respect to xl you can say, and times this much. Okay. Now let us multiply the terms inside this bracket with this dxl by ds. So this will be del aj by del xl times dxl by ds minus this Christoffel symbol times am dxl by ds. But you definitely have an idea of partial differentiation. So from the idea of partial differentiation, can you say that this product del aj by del xl times dxl by ds can be written what? This can be written as daj by ds. Okay. So the intrinsic derivative of the covariant vector aj with respect to s, which is denoted by this symbol delta aj by delta s, that is equal to daj by ds minus this gamma m jl am dxl by ds. Okay. So in this way we can find the intrinsic derivative of a covariant vector. Okay. Now we will define the intrinsic derivative of a contravariant vector. The definition is same, the technique will be same, and so for defining the intrinsic derivative of contravariant vector, let us consider that this Aj, that where J is the contravariant index, this is a contravariant vector. And with respect to S, its intrinsic derivative will be denoted by this symbol delta Aj by delta S. And in accordance with the definition, this intrinsic derivative of Aj with respect to S will be defined like this. Here, this Aj comma L, what is this? This is the covariant derivative of contravariant vector Aj with respect to XL, okay, and times dXL by ds. Again, you can remember your previous you can remember my previous lecture, and where you have seen that this covariant derivative of the contravariant vector Aj with respect to XL in terms of the Christoffel symbol is defined like this. Okay, this is del Aj by del XL plus this second kind Christoffel symbol times Am times dXL by ds. Again, this can be written as del Aj by del XL times dXL by ds, and this second term. Okay, and again, from the idea of partial differentiation, this product can be written as dAj by ds. So in case of contravariant vector, the intrinsic derivative is defined by this equation A2. Okay, mark the difference here. There is minus sign before this second term, but in this case there is plus sign. So you have to mark it. Okay. Now we will see what will be the intrinsic derivative of an invariant. When you say invariant, that means a scalar. Okay. And for this we consider that this phi is a scalar, and we have to define its intrinsic derivative with respect to S. So symbolically this will be written as delta phi by delta S. And from the definition of intrinsic derivative, this will be equal to covariant derivative of phi with respect to XL times this dXL by ds. Okay, but that the covariant derivative of covariant derivative of the scalar or invariant with respect to XL is defined as this partial derivative del phi by del XL. We have learned earlier, and times this much. So again, from the idea of partial differentiation, this can be written as del phi by del S equal to d phi by ds. So see here, this is a very interesting result, and all these results are very important, particularly for objective type questions in your examination. What is this d phi by ds? This is simply the ordinary derivative of phi with respect to S, or you can say the total derivative of phi with respect to S. So the intrinsic derivative of the scalar or invariant phi with respect to S is simply equal to the ordinary or the total derivative of phi with respect to S. Okay, so this is a very important fact. Okay, now we will see the intrinsic derivative of the three fundamental tensors, and for this you must remember the previous result when I have discussed the covariant derivative of fundamental tensors. Then you have seen actually the covariant derivative of all the three fundamental tensors are equal to 0. Okay, and so here we will again find that the intrinsic derivatives of all the three fundamental tensors will be 0. But how you can see? First of all, we are going to see this covariant the intrinsic derivative of the covariant fundamental tensor, this G subscript jk. You know, G jk is the covariant fundamental tensor. And if your aim is to define its intrinsic derivative, the symbol will be what? The symbol will be delta G jk by delta S. And now, in accordance with the definition for finding the intrinsic derivative, we will have to take the covariant derivative of this G jk with respect to XL, which is denoted by this symbol G jk comma L. And then we will take the inner product of this G jk comma L with this G dxl by ds. But we have learnt earlier, and I have told just now, that the covariant derivative G of the covariant derivative of the covariant fundamental tensor G jk is equal to 0. So if it is 0, its intrinsic derivative will be also 0. Okay. Similarly, if you are talking about the contravariant fundamental tensor G superscript jk, then its intrinsic derivative will be denoted by this symbol, and this will be defined as the product of this covariant derivative of G jk with respect to XL times dxl by ds. But we have also seen that the covariant derivative of the contravariant fundamental tensor is also equal to 0. So its intrinsic derivative is also 0. Okay. Now, if you will talk about the mixed fundamental tensor G superscript j and subscript k, then its intrinsic derivative with respect to S will be denoted by this symbol, see here. And this will be equal to product of this dxl by ds with the covariant derivative of this G jk with respect to XL. But this covariant derivative of the mixed fundamental tensor is also 0, so this result will be also 0. So finally, we see that the intrinsic derivative of all the three fundamental tensors are equal to 0. Okay. So this is just a brief idea of finding the intrinsic derivative of a tensor, and when it will be used, then you will see that it is a very important concept which will be used vividly while studying the course on general relativity. Okay, thank you very much.